provides x bar minus mu, which is assumed to be both the mean of the underlying distribution that you're drawing from, in this case, the mean of the distribution of the population you're drawing from, and your sampling distribution of x bars, and divide that by x bar minus mu divided by standard deviation divided by the square root of n. Here's the big bang of central limit theorem. Note that it doesn't say anything about normal population. I started to say that a minute ago. Drawing the random sample from a population with mean, mu, and finite standard deviation sigma doesn't say normal, doesn't say binomial, doesn't say exponential, doesn't say anything. Any distribution you're drawing from with a mean of mu, finite standard deviation of sigma, central limit theorem gives you then, you go to the next slide, provides a basis for approximating the distribution of sample means with a normal distribution with a mean of mu and a standard deviation, as we've been saying, sigma over the square root of n, the size of the sample you're taking. The approximation gets better as n gets larger and larger. Okay, so that's the central limit theorem. The manufacturing process produces parts with a mean diameter of 5 millimeters. An engineer conjectures that the population mean is 5.0 millimeters, and an experiment is conducted in which 100 parts are selected at random and measured. It is known that the population standard deviation, sigma, is equal to 0.1, and the experiment indicates the sample average diameter, x, and that should say x bar, is equal to 5.027 millimeters. Does this refute the engineer's conjecture? Okay, so the engineer says, hey, 5.0 millimeters. Take a sample of size 100. Additionally, it's known that the population standard deviation is 0.1. And an experiment, out of the sample that's drawn of 100 parts, the sample mean is determined to be 5.027 millimeters. So the question is, does this support the engineer's view or not? And whether or not the data support or refute the conjecture depends on the probability that data similar to that obtained in this experiment or this sample drawn can readily occur when the mean is, as he or she says, it's 5.0. How likely is it that you could obtain a sample mean that is 5.027 or higher when your sample size is 100? Okay, that's the question. And when the true, when the mean is 5.0, as the engineer can suggest. So the probability that we choose to compute is given by x bar minus 5 is greater than 5.027. And this is the same thing as asking if the mean is 5.0, as the engineer indicates, what is the chance that it will deviate by as much that the sample that we draw and the sample mean will deviate by as much as 0.027? Okay, so there's a conjecture that it's 5.0. We take a sample. That sample turns out to be 0.027 higher or larger than the conjectured average that the engineer suggested. So we look through and we say, okay, the sample x bar minus the conjectured mean 5.0 divided by the standard deviation of the sampling distribution 0.1 divided by the square root of 100. 100 parts were sampled. Turns out you need a z. What's the probability that z is greater than or equal to 2.7? And that point turns out to be 0.0035. So there was a 0.0035 chance that we would have drawn a sample that would have been 0.027 above millimeters above the mean of 5.0 if the engineer's conjecture is correct. Another way of saying that, thus one would experience by chance a sample mean that is 0.027 millimeters from a population mean in only 3.5 of 1,000 experiments. Therefore, that's a very remote chance of getting that particular sample if indeed the average is 5.0. So it doesn't support it. And in fact, to me, I would interpret this and say it seems like it would be higher, it would be larger than 5.0. Not saying what that would be, but with a 0.0035 probability that a sample mean would be greater than or the deviation from the sample, or the 2.027, your sample mean would be that far above a 5.0. Very remote chance that you would draw that. So it didn't support conjecture. Okay, so moving on. You may have picked up that so far I've been saying, okay, what would be the probability distribution of X bar when the standard deviation of the underlying distribution is known? I've been saying that quite a bit through all of this with the central limit theorem and some of these other things. Known standard deviation of the underlying distribution. And you might ask, well, is that very realistic or not? And what if you didn't really know the true population standard deviation? Well, here's the answer. If your sample size is considered large, which is 30 or more, then everything about that normal distribution, the sampling distribution of your sample means, follows a normal distribution, still applies as a good estimate for the sampling distribution. If your sample size is smaller, however, size 30 or less than 30, then a good estimate for the sampling distribution of sample means instead turns out to be something called the t-distribution with n-1 degrees of freedom. And so let's take a quick, brief look into what is a t-distribution. The first view of it, what we're looking at is noting that as this is a two different t-distributions, and you notice that with the degrees of freedom equal to 1, there's quite the tails are what are called fat, which means there's more variability in this distribution. T-distributions are like normal distributions where they're symmetric, they're bell-shaped around the mean, but they are more variable than a normal distribution. So you'll see out there -4, +4. As you look beyond that, it's wider. And what happens is you look at the purple line, degrees of freedom of 2, there's less variability. With the light blue one, degrees of freedom equal 5, which suggests there's sample sizes of 6. Your sample size is going up. There's not as much in the tails, and it's getting less and less, a smaller and smaller standard deviation. Another kind of way to look at t-distributions, they're more spread out than the standard normal. So the light blue, in this case, is the z-distribution, the standard normal. T-distribution with n close to 30, you see it's quite fat in the tails. There's more variability in the t-distribution. And when n is less than 30, there's quite a bit of variability in the t-distribution. And, what you're accounting for is, A, you're drawing from any population. You no longer know the standard deviation associated to the underlying population, and you're drawing smaller samples, so you're not getting as much information. So what the t-distribution does is it gives you that more variability in the definition of what your sampling distribution for the sample means will look like. And so you work with the t-distribution when you don't know your underlying standard deviation for your population. Okay, so sampling distribution of X with an unknown sigma. So this is the formal way to look at it. Let X1 through Xn be the independent random variables with the normal that have a normal distribution with mean mu and an unknown standard deviation sigma. Let x bar be, just as we've calculated, sum up all the values, divide by n to get the sample mean, and let the sample variance be just as we've defined it before. Then the random variable t, x bar minus mu, divided by, now, on the bottom part, you're working with a sample standard deviation instead of sigma, because you don't know sigma anymore, divided by the square root of n, has a t distribution with n minus 1, and presumed to be less than 30 degrees of freedom. Okay, so on this topic, you go to the Blackboard again, and there's some exercises proposed that you can go and look at and work on for when you do not know the standard deviation and you take small sample sizes. Okay, at this point, I'll take a break, and we'll come back and cover the sampling distribution for sample variance in the next recording session.